All good? All right, so thanks to everybody. My name is Spencer McIntyre, and we are here for the Fun with Dr. Brown talk. So, all right, quick introduction. I am Spencer McIntyre, security researcher at Secure State, and Metasploit project member. Very happy about that. And this is Dr. Brown, Dr. Emmett Brown, which is who we're going to talk about today. So we're actually going to be talking about Microsoft's Emmett. So pretty cool stuff I have to talk to you guys about here today. And so thank you for staying with me. So real quick overview. I hope everyone's pretty familiar with what Emmett is, with what it does. So I'm going to try to not rehash that. I want to skip right into the good news stuff. Basically, Emmett is Microsoft's answer to trying to prevent exploits for vulnerabilities that are not yet known. So it makes them very difficult to exploit. It does not fix vulnerabilities, it makes them difficult to exploit. It's Microsoft's Enhanced Mitigation Experience Toolkit. So it's an application, you download it, you run it, and it provides a bunch of different protections to a bunch of different applications that have a bunch of different flaws that we all know and love, such as Adobe, Java, Microsoft, Internet Explorer, Word, all that good stuff. So it helps you to protect that. So I want to really stress, Emmett does not fix vulnerabilities. It just makes them much more difficult to exploit reliably. So we're going to talk about exploit reliably, however, crashes, because if you trigger an Emmett exception, it's going to crash the application. So DOSes are still plenty. Worst case scenario, you can still kill the application all day long, but everyone pretty much knows that if you can't exploit the application in order to take control of it, then it's not really doing you much any good. So you can still get DOSes out of it. The latest versions right now, there's kind of two going on. There is Emmett version 4.1, which is what Microsoft has deemed is ready for production. So if you are running Emmett in a production environment, they recommend that you use 4.1. However, there's also 5.0 Tech Preview number 2. There is a Tech Preview number 1, and we'll talk about that a little bit later. But 5.0 Tech Preview 2 is the latest one. Microsoft does not recommend running that on your production systems, on servers, things like that. But it has some new features, a lot of improvements, things like that. So, all right. So I am very, very offensive focused. I like the offensive security and the technology. I know every time I come to these presentations, it seems like everyone always wants to talk about defensive stuff. So if you're like me, you'll appreciate the fact that I have color-coded my slides. Green ones are kind of neutral. Blue ones are going to be when I'm talking about the defensive stuff, and red ones are going to be the offensive goodies, the details of the exploitation technique. So feel free to tune out whichever one if you don't want to listen to them. But real quick, this is what Emmett provides to how it makes exploits more difficult to target, to exploit. So this is not all the protections. This is certainly not all the protection, but these are the key ones. These are the ones that are going to affect most of the situations. So there's depth, which has, of course, predated Emmett along with ASLR. Those are the ones that we all know that you can actually use those settings without Emmett even being on your system. Those are built right into the operating system in modern versions. So if you have like XP, SP3, and newer, you have options to have DEP on your system. They've made a bunch of different improvements to DEP in the ASLR implementations. So Windows 7 is still going to be a lot better off, but you can use these settings without having Emmett on your systems. Emmett does make it much more easy to configure them, though. So you can see the settings, you can toggle them, because there's multiple different settings. Specifically for DEP, you can have it completely off, completely on, and then you can give the applications the option to opt in and opt out. So you can trigger and toggle all those different things using Emmett, which is pretty nice. There's also the null page protection, which helps against local kernel exploits, typically what that's for. Stack pivot and the export address filtering. The export address filtering is probably one of the cooler protections. It's actually targeting shellcode. It makes it more difficult, and you have to sort of work around the export address filtering in order to get your shellcode to work, which causes a lot of stock exploits that utilize the Metasploit framework for their payload sets to not work, because these payloads are not built to bypass the EAF. So that's why those don't work. So it makes them difficult to exploit. So this is a screenshot. See, the text is kind of washed out there. But if you see all those different little checkboxes, those are all the different settings that you can toggle on a per application basis. So you can build a profile, and you can target specific applications. You can say, I know this is really, really sketchy software, so I want to turn all the settings on this one, whereas heap spray makes Java not work, so you might want to take that protection off of Java, things like that. So you can have real fine-grained control over that. DEP and ASLR, this is exactly what I was talking about before. These can be configured by the operating system. So if you see that up in the upper right-hand corner, you have the different settings that are available. So DEP, ASLR, SE, hop, and certificate pinning are like 4 special settings that you can actually configure up in here, as well as toggle them on for each individual application. But those ones have more advanced settings. So we're not really going to talk about those because it's sort of out of scope for the talk. I hope everyone's pretty familiar with what DEP and ASLR at least do, or at least try to do. So another key point that I want to make is pretty much XP is end of life. Nobody's really using it. Nobody has time for that anymore. Windows 7 is sort of the new standard. We're seeing that in most of our target enterprise environments, and then some Windows 8 and some of the more advanced ones. But so for the talk, we're going to assume that we're primarily going to be focusing on Windows targets. And since Windows 7 came out, Windows 7 SP1, almost all of the native DLLs, all the native executable modules that are distributed by Microsoft have ASLR enabled, which is very important, which is what we're going to talk about for some of these attacks. It's really the third-party applications that you need to be worried about. Things such as Firefox, Java. Java is notorious for this, the Adobe products, things like that. So those are the ones that are going to introduce modules that may not be ASLR. Java's gotten a lot better, and so has Adobe, but if you download and install games, quick notepad programs, things like that, anything else where the developer's not really from a credible, security-conscious organization, they may or may not have these settings enabled. It's kind of a problem for that. All right, so bypasses for Emmet are not a new thing. They've been around for a while. So the first one up is ASLR and DEP bypasses. Currently, the most common techniques are, if you want to bypass ASLR, pick a module that's not ASLR. It's pretty easy. So you really just need one. The more that you have available, you can use those. And then to bypass DEP, pretty much you use the Windows API to turn on and off the protection. So these are all the techniques that we're all very, very familiar with. These all predate Emmet itself, because of course these protections predate Emmet. So not really there, but I want to point those out because those techniques are still applicable when Emmet is in the environment, or when Emmet is in the equation and protecting the application that you're targeting. So one of the techniques that I see sometimes is Emmet implements its protections via hooks. It will hook key functions that are used commonly by exploits, and it will run analysis when those functions are being triggered to tell and see if a malicious user or the threat is malicious in intent to trying to use that code. So one of the popular techniques I've seen to get around these is to simply jump over those hooks. While those work in some key edge situations, primarily if the deep hook setting is off, that does sometimes make the exploit target a specific version of the Windows DLL that that the protected function is contained within. Because when a lot of the functions, the primary functions such as write process memory, virtual alloc, virtual protect, those things like that, once the function is executed, it's actually a very short stub that calls another one, typically the same function but the EX version, the virtual protect X, things like that. So the stubs, the assembly in the code is not always the same. So if you jump over that, you need to know what that is, and that's going to make the function, the exploit, dependent on the version of Windows as well as dependent on the version of DLL. So while this technique works if you know everything there is to know about the environment, this could be a proper technique, it doesn't really work for real-world type attacks because we don't always know that information, and we don't want our exploit to be dependent on the Windows and DLL versions because that's never really a good idea. It makes them very unreliable. Unfortunately, I could not find a resource that was the first mention of this technique. So I know it's one out there, a lot of people talk about it, but I could not find the oldest reference to it. I spoke about export address filtering a little bit earlier, Emmet's EAF protection. And Skyline had a fantastic white paper that was published in 2010 that discusses how to build your shellcode which will bypass the EAF filters. And that was targeting Emmet version 2.0. So that is a fantastic resource, and I believe the techniques to bypass the EAF are still kind of the same, although Microsoft has integrated in additional protections and sort of strengthened up the EAF protection. So those are the previous techniques. So what we're here to talk about today is a technique that I found that affects Emmet version 4.0 and 4.1 and actually 5.0 Tech Preview 1. We're going to talk about that and how that can actually be used. So I have disclosed these details to Microsoft, and they have addressed it. It is completely fixed in 5.0 Tech Preview 2, but this is still relevant for 4.0. And like I had mentioned earlier, Microsoft is still recommending that if you have a production system, you use Emmet 4.1. So a little bit of background. When Emmet starts up and it is protecting an application, it loads the Emmet DLL into the application that it is protecting. As part of that DLL's load routine, it gathers the configuration from that GUI that we saw earlier. All of those settings are stored in the registry. When that DLL starts up, it copies those settings and the configuration into the address space of the application that it is protecting. So it has the configuration and it knows what to do. This is a very key point. This is what we're going to be harping on pretty much for the rest of the talk, is that this configuration is copied into the .data segment of the Emmet DLL, and that segment has read and write permissions. So the application can modify it at runtime, and that is exactly what we are going to illustrate. We are going to modify the configuration so that we can get our exploit to work. So real quick, we need to pick a vulnerability to actually use this technique with. So our vulnerability is going to be a vulnerability in an application that will be protected by Emmet. So things that we need a large amount of payload space. The reason why is because the original payload, the original exploit, is going to need to have additional space because we need to add in additional ROP gadgets to make the changes in memory necessary for the configuration to be corrupted. We need to have no bad characters because we need to have the ROP chain has to pull from gadgets from the executable itself or from different DLLs. But because Emmet provides ASLR on all the different modules, in an application specifically that we are targeting, the executable itself is the only module that is not protected by ASLR, and there is a null byte in that address space because, of course, it loads up into the standard 40 address space. And so we need to have no bad characters for this. So, and then, like I said, we need to have at least one non-ASLR. So we're still going to use the same technique of bypassing ASLR by picking a module that does not have a random base. So the one that we came up, the one that I ended up using was CVE 2013-2492, which is probably not a very common exploit, but it is a remote stack buffer overflow in Firebird FTP server. There is a public exploit for this. It is in the Metasploit framework, and it has all of these desirable qualities as well as being remotely exploitable for system privileges on a default configuration of Firebird. So that is what we ended up choosing and why. So as this comes up, all of those protections that we discussed earlier do not protect against every single type of vulnerability. For example, the null page protection specifically targets local exploits that have a use after free vulnerability where the application will map the null page and then use that to have a corrupted data that will be used when a pointer is referenced after it has been freed. That has absolutely nothing to do with the stack-based buffer overflow that we're going to use in CVE 2013-2492. It has nothing to do with that, so that protection is not really applicable for this. So these are the protections that do in fact stop the current exploit as it is from running. Like I mentioned already, the public exploit already bypasses DEP and ASLR using public well-known techniques, so that's sort of out of the picture. But these four protections are the protections that are provided by Emmet that are actively blocking the exploit from working. So we have the caller protection, which is Emmet determining where the function that is being protected is being called from. It examines the stack to ensure that everything looks legitimate. Basically, that the instruction that is next from the return address or previous to the return address is a call instruction to that function, which helps prevent against ROP chain attacks, things like that. The deep hook setting and the banned functions, and banned functions is just specifically protecting against functions that are commonly used in exploits by the ROP chain to modify stack permissions, things like that. All right, so as I mentioned before, we have access, or the application that we are targeting has access to modify the configuration of Emmet. So when we look at this, we want to determine what do we want to modify. Well, the first thing that comes to mind is the default action that Emmet takes. This default action is what happens, or what Emmet does, when one of the protections are triggered. It defaults, of course, to stop on exploit. What that is going to do is when Emmet determines that something bad is happening, it is going to kill the application, which is why I mentioned earlier you can still have a sort of denial of service condition, but it's not really good enough for us. Or you can have it audit only, which is going to create a log message saying this application did something fishy, you probably want to take a look at it. Well, by default, it is stop on exploit. So what we're going to do is we're going to modify our exploit to change that setting and turn it off. We want it to audit only so that our shellcode can run along its merry way and give us a payload, or give us a session. All right, so we're going to patch the default action via ROP. So the emit, so this brings us to our first conundrum, which is that that data is stored in the .data section of the emit DLL. The emit DLL is, of course, ASLR. So what we do is we ended up actually resolving the base address of emit via a call to get module A. So get module handle A is not a protected function, which means that we can use that to resolve the address to emit without hitting any of those previous protections that we had talked about, such as caller or ban functions or anything like that, because it is not a protected function. It's innocuous. A bunch of programs use it. It has nothing. A lot of shellcode use a similar technique, but we can use that to bypass it, because at this point, when we call this function, emit is still active, and it would block us if we did something that it found to be fishy. So we use that to resolve the base address of emit, and then we calculate out the static offsets to the data segment that contain the key configuration values that we want to change. These are the 2 pointers that I determined that are going to be ones that we want to modify. The offsets are actually the same in emit versions 4.0 and 4.1, which is fantastic because we can have a single exploit with a target that will affect 4.0 and 4.1. Fantastic, because otherwise we don't want to have to know yet another thing about the target, such as the emit version, the Windows version, the version of Firebird. That's too much stuff. So being able to have one that targets both emit 4.0 and 4.1 is fantastic. All right, so if you look at this, this is the Vivisect disassembler. This very top push instruction is a reference to the exploit action string. It's in Unicode. So this is the disassembly of the DLL itself. Now, this next offset right here is one of those offsets I had just mentioned earlier. And if we look at the references to it, if you see there's a pattern that is in there that pretty much, not all of them, but a lot of these are comparing the value that's at that address to 1. So it is comparing that flag. In terms of the C code, that would essentially be an instruction saying, if exploit action, then do whatever. So it's just a Boolean value. It can be on or off, basically defining whether or not it should stop on action or audit only. So that's what we are looking at, and that is the value that we're going to change, so it always evaluates to what we want it to, which is, of course, going to be audit only, so it won't stop our stuff. All right, so this is the actual, you cannot see that at all. So I will walk you through this. This is our actual ROP chain. It is 19 gadgets total, built from the single executable module that's not ASLR, of course, so we're building it up from that. And the basic steps at a high level of what it does is it resolves the emit base address via the get module handle A function that we had mentioned. And it calculates out the offsets to those 2 offsets. It calculates the first one, then via ROP, it overwrites that value, sets it to 0, calculates the value to the second one, and once again, overwrites that value as well. So that way, after that is done, we have essentially switched the default action from stop on exploit to audit only. After that, what is fantastic about this is that we can have our original exploit run along its merry way in the exact same way it was before, essentially unmodified. Because when emit triggers its protections, when emit triggers its protections, it's going to check that default action and is not going to stop it. It's going to continue to run. Now, the reason why we had 2 pointers actually is because the first time that I had done this, I determined that you could switch it from stop on exploit to audit only, but it still logs a message into the event log. So it goes into the Windows event log and it says, this application had a failure for the caller protection, and it logs an event message in there. Not very good. So the second pointer, actually, the second value that we change actually disables the logging. So between the 2 of them, we can have both it turned off to audit only, but then it doesn't audit at all. So it's essentially completely silent, doesn't log anything, doesn't pop up a message, anything like that. Runs along its merry way, and it doesn't stop us. So we can now run straight through all of the protections that Emmet has that it would normally trigger and stop the application, and it does not stop. So we don't have to modify our payload, so we can use nice Metasploit payloads, which the original one always used. And energy required, less than 1.21 gigawatts. Fantastic. All right, so demo time. So this exploit is memory corruption, and like I'd mentioned, the entire job of Emmet is to make exploitation very difficult to exploit reliably on vulnerable systems. So I actually have a video that we are going to show you. It's really nothing special. The final product is just a Metasploit module with an additional target that says Emmet. So just hold on up here. Okay, so a little bit of background. This black screen in the back is PuTTY. This is PuTTY'd into the attacking system. And then this is Emmet that we are actually showing that is protecting the application that we are targeting. Okay. So as we can see right here, all the protections are enabled. The default action is stop on exploit. That is our process. Showing the IP address, pretty much the look ma no hands moment. The exploit is very quick, which is also very nice. So if we look at it, what it did is we had our modified ROP chain, which executed our instructions to switch that default action and then continued to then to set our payload to be executable and then jump back to it to execute, which is what the original one did. So we did not have to modify any of that. So that is what has taken place. And of course, afterwards, the result is a shell as NT authority system. It's everybody's favorite. And we can tell that it's on the same host. Okay, so if we look at this right here, the process that it's actually protecting is 908. And if we refresh it, that process is still running. So that's still the one that's running. So the exploit did not cause the server to go down. But if we run, just here in a second here, it's going to run git pid. And it's going to show that the process ID of where the session is actually running is not actually the same. The reason why that is not actually the same is the prepend migrate option that Metasploit has built in now prepends a option to migrate the shellcode out prior to the main payload running into a new process. When using Emmet, this option is very, very helpful because you can migrate into another process that is not protected by Emmet, which makes the exploit slightly more reliable. So that's why the process IDs did not match up. The prepend migrate, if you're using a blind exploit and you have no knowledge, you know Emmet is on it, but you have no knowledge of the configuration, setting prepend migrate to true is actually kind of a good shot in the dark, because if only one or two of the protections are enabled, such as if only like EAF is enabled, prepend migrate has a good chance of being able to get around that, assuming that the Emmet is not configured to protect absolutely every application, because it is going to start a new process of, I believe it's Notepad, and then inject itself into that. So if Notepad is not protected, that is where your shellcode is actually going to be executing. All right. Okay, so like I mentioned, this all affects Emmet versions 4.0 and 4.1. So I disclosed these details to Microsoft actually a couple of weeks before 4.1 came out. They didn't have enough time to change it, or I don't think they took me seriously. They're just like, cool story, bro. But they didn't do anything about it in that time span. I did, however, eventually get a response back from them, and I've emailed them back and forth multiple times, and they've been very helpful after that first email. But anyways, 5.0 TP2 came out, and they said, hey, we fixed it. So I took a look, like every good vulnerability researcher does, to see, did you really fix it? So if you look at this, this is the assembly of where it is actually checking the configuration. You can't read this, but this little pink function right here, It is the function decode pointer, which is provided by the Microsoft API to obfuscate pointers at runtime to critical sections. The Emmet configuration is a critical section because if you can modify that, of course, as we just demonstrated, you can pretty much negate all the effects. So what's really nice about this decode pointer is that just above it, there is another pointer that can be checked against 0, and based on this value, you can determine whether or not that function gets called and where that is actually stored. So what do? We disable that too. So in disabling that, we set it so that it is not calling decode pointer, so it is accepting the pointer as being the actual location, but we can't modify the existing configuration. In fact, we don't even care where it is at this point, but we disable that, we write in a pointer that is plain, and then we point that pointer to a location that we know is predictable, that we can set the values to once again, so that those values will be interpreted as the Emmet configuration. So that still works as well. So went back to Microsoft, told them that the decode pointer, fantastic idea, but the ability to be able to turn that off, probably not the greatest idea. So this is the same function in Emmet version Tech 2.0, or Tech Preview 2, and this little pink right here, that is the new location of the decode pointer function. As you can see, there's no jump instruction around that, so it does have to go through that. This is a fail out. This right here sets EAX to 1 and fails out the function. So this won't work because that will stop it, but we have to go through this section right here. So now the location of the configuration is obfuscated, as well as the configuration itself is now marked in a location that is marked as read only. Well, we could mark that as writable. However, a lot of the functions that are required to mark and change the permissions are protected by Emmet. So you kind of have this sort of what comes first, the chicken or the egg problem, because in order to change the protections, you'd have to run through Emmet. Like I said before, the original function that modified the configuration, the only API function it called was get module handle A, which is not protected, which is why that wasn't an issue before. However, in order to change the permissions on the page so we could modify it and turn it off again, we would have to run through a protected function. So it makes things a lot more complicated. The only thing I can really think of at this point in order to get around this is that you would have to be able to resolve and call encode pointer within the module. So being able to get around this at this point, you would have to have a module that is not ASLR, that is the executable, that has a pointer to the encode pointer function in its import address table that you could pull out from a predictable locations. That way you could overwrite the pointer. That's just an idea. I wasn't able to do it. So the entire idea of Emmet is to try to make things more and more difficult. They're raising the bar. So in this case, I'd say it's pretty well done. All right, so like I said, the configuration is no longer stored in the data section. It is allocated, and then just that encoded pointer is stored in the data section. And then the configuration is then protected. It's a read only, so you can't write to it, you can't modify it. And that's pretty much it. Yeah, so you would, in order to be able to get around this, you would probably want to write to the pointer that's stored, the encoded pointer. You'd want to write a new value that you would be able to control. In order to be able to do that, you'd have to have the encode pointer function. You'd have to be able to resolve that at runtime. So just some closing thoughts, some of the things that I learned from being able to mess around with this. Main executables without ASLR is apparently bad. From having spoken with Microsoft, they consider that to be the worst case scenario. If the main executable is not marked as ASLR and ASLR, the setting is cranked up to the max, that module is still not going to be at a random base. Emmet can't do anything about it, which is why in our exploit, we were able to still pick on that primary executable, which is just bad development, really. Emmet's deep hook setting, also a fantastic option. I hear it breaks a lot of things, though, which is why it is no longer on by default, but I have read on the security blog from Microsoft that they are considering returning that back on as the default setting as they work with third parties such as Java, Adobe, to make their applications work with that. The prepend migrate in Metasploit, that's just a payload option. If you have any of your staged payloads, or I believe any payload at all, you can set prepend migrate to true. And it's going to make the payload a little bit larger, but it is going to start a new process that hopefully will not be protected by Emmet, and then run your shellcode in that new process. Very quick and dirty trick to try to get around it. And like I said, this technique it's not a silver bullet. It's really not. From an exploit development perspective, that's a lot of criteria you really need to meet in order to be able to get this to work. So the selection for a vulnerability to demonstrate this vulnerability in Emmet, it's pretty tough because you have to have a good amount of space, no bad characters. Primarily, the main executable needs to not be ASLR'd, and you need that function get module handle A to be in the IAT of the non-ASLR module. That's a lot of stuff that you really need. So this is not a silver bullet. However, if you do have all those criteria, you can get around it. This is a timeline that I sort of put together. So Emmet 4.0 released in June 17th, 2013. So all of those versions, I did not check Emmet 3.5, but all of the ones that should be in production, according to Microsoft, of Emmet 4.0 and 4.1 are affected by this issue that you can corrupt the configuration to bypass it. This is when we notified them. And then this last one, right on down here, I want to talk to you about just a little bit. The fine gentleman over at the Offensive Security, they have a fantastic blog. On July 1st, they posted a technique that was very, very, very similar to this. So similar, in fact, that my contact at Microsoft emailed me asking me if I had written it for them or if I worked with them. Offensive Security used an Internet Explorer exploit to disable specific protections on Internet Explorer at runtime in order to get their exploit to work. Awesome. They actually go on in the blog a little bit later to say that they checked the latest versions of Microsoft or of Emmet, and it appears that Microsoft is aware of the issue and has addressed it. So, thanks, guys. Fantastic resource, though. All right. And does anybody have any questions? Nope. Nothing? All right, cool. These are some of the best resources and references I could find on some of the latest Emmet stuff. This is the Offensive Security blog I had just mentioned, and Exodus Intel by Aaron Portnoy is a fantastic read for anyone. If you don't know anything about Emmet at all and you really want to know about bypassing all of the things, fantastic resource. It goes into a very in-depth technical detail about each one of the protections, how they work, and how you can get around them. So, all excellent, excellent stuff. And thanks for your time. Spencer.